Okay, so this was part of our warm-up, and then we'll take a look at that proof that we had as well. Just kind of a refresher with radicals. We will have radicals introduced once again into this unit, and then also in our right triangles unit. And although this was Algebra 1 and we reviewed at the beginning of the year, I think it's always good for us to re-review it, because some of us kind of forget our properties. So with letter A, we have root 3 plus 2 root 3 plus root 7. Can I combine any of those together? Yeah. So for radicals, we have to have what are called like radicals. It's kind of like terms. If this was x plus 2x plus y, we can only combine the x's together. So likewise, I can only combine my root 3's together. So what is root 3 plus 2 root 3? If I have 2 root 3 over here and another root 3 over here, how many do I have in total? 3 of them. So I have 3 root 3's plus root 7. You can think this is 1 root 3 if that helps. So when we're adding radicals, again, just how many radical 3's do I have? Now I cannot combine root 3 and root 7 because they're not like radicals. This will be your answer here. Give me a thumbs up if you get that. Very good. Okay. So with letter B, we now know, or we have reviewed, that we can add together a root 3. So I know that I have a 2 root 3. And then what do we get for 3 plus 6? 9. Now, can I add together the 9 and the 2? No. So once again, these are not like terms. We have a whole integer, and here we have an irrational number. So this would be your answer, 9 plus 2 root 3. You could have written it as 2 root 3 plus 9. That would have been fine, but it's more proper to write that integer first, just so you don't think that that plus 9 is underneath the radical. Okay, any questions on A or B? All right. So letter C, what should we do first here? We actually have a couple ways we can go about this. What do you guys want? Yeah. Order of operations, we should simplify inside parentheses first, if at all possible. So this is really 3 times, let's see, we got 4 and 1, so 5 root 5. Good. So now what do I do? Obviously we have to multiply, but is it 3 times 5? Is it 3 times the 5 underneath the radical? Or is it 3 times both of them? What do we do? Go ahead, Ryan. Very good. We can only multiply what's outside the radicals together and then what's inside radicals together. So I would have 15 root 5, and I cannot do anything more with that. Good. The radical protects what's inside of it, so we cannot touch underneath the radical unless we have another radical. Right. You could have also distributed this and gotten 12 root 5 plus 3 root 5. Which gives you 15 root 5, but probably easier to simplify in some ways. All right, and then letter D, you guys are usually pretty good with this. So with letter D here, what do? I have root 6 times root 3. How do I go about this one? Root 6. Good. What's underneath the radical gets multiplied together. If I had numbers outside, I could multiply those together as well. So I have root 18. Am I done? No, we can simplify it down. So this breaks down into 9 and 2. 9 is a perfect square, 2 is a prime. So square root of 9 is 3. Square root of 2 we cannot do. 2 is underneath, so we get 3 root 2. All right, give me thumbs up if you got that last one. Awesome. Give me thumbs up if you got all 4 of them correct. Very good. Very good. Okay, so again, just a reminder for D, say it was 2 root 10 times 3 root 2. We would multiply the outsides together, and then I would multiply my insides together, and then I would want to simplify from there. So this would give me 6 times 2 root 5. So that's the bonus one. Okay. Any questions on those? Okay. So remember, integers and radicals cannot be combined together. You just have like radicals more times. Okay, this doesn't work. All right. So let's take a look at our proof that we have. This is kind of building upon what we did last class. Last class we learned about our special parallelograms. We have rectangles, rhombuses, squares. Ooh, that was rough. And we had our properties on those. So here we have ACDE is a rectangle. So ACDE we have as a rectangle. And then they tell us that ABCE is a parallelogram. So ABCE is a parallelogram. And they wanted to show that ABD is isosceles. This big guy here is isosceles. Alright, so it's a lot of overlapping lines to work with. So let's take a look at where we need to head. In order for ABD to be isosceles, what do we need? Yeah, we need two of our sides or legs to be congruent. So if we can accomplish that, then we can have it's an isosceles triangle. That right there automatically reduces down the number of paths we can go down. Because if we need our legs to be congruent, then we need to look at sides congruent. So we're limited really to just our sides congruent. So let's take a look. Well, probably should start out with statements. So ACDE is a rectangle. ABCE is a parallelogram. Alright, I want you to go and compare it with your shorter partner real quick. What was your next step that you did? Actually, compare the next two steps, because perhaps you did one before the other. Alright. So we have given to us ACD is a rectangle and ABCE is a parallelogram. What was one of the next steps that you guys? Go ahead, Vincent.
BC is congruent to AB on opposite sides of parallelogram.
I like that. So Vincent said EC is congruent to AB. So EC and AB are congruent because opposite sides of parallelograms are congruent. Oops. Opposite parallelograms. Opposite sides of parallelograms are congruent. Very good. Alright, and notice he's already pulled into that one of the sides of the triangular. Good. Alright, what's another thing that we could have done? Or perhaps the next step after this. What did we do next? Go ahead, Ryan.
I said BC and AB are congruent.
Got BC and AE are congruent. Alright, and what's your reasoning for that?
No, East.
Sorry.
You meant the diagonals.
You want the diagonals congruent?
Oh, you just did what I said. Okay, so I did AB and EC.
Good. So we have AD and EC. And how do we know that those are congruent?
Diagonals of a rectangle.
Good. Diagonals of a rectangle are congruent. Diagonals of a rectangle are congruent. Good. And notice with that, we've gone ahead and brought in another side of our triangle here. So although we know that opposite sides of parallelogram are congruent, we really only needed one set of those opposite sides. We didn't need A, E, and B, C. And likewise with a rectangle, in stating that our diagonals are congruent, we could have said opposite sides are congruent, but again, the opposite sides of a rectangle or not necessary for our isosceles triangle there. So good job identifying which pieces pull together. Okay, what's going to be my next step? You guys are pretty much there. Noah, what do you think? What should we do next? Good. We've got AD is congruent to AB. And Julia, why do you think that is? Yeah, substitution or transitive property. Good. Alright, so now that we have AD and AB are congruent, now we can take it home and say that triangle ABD is isosceles. And what would be my reason for that? What do you guys think? How do I know that that is isosceles? Yeah, definition of isosceles triangle. Isosceles triangles, two sides are congruent. We have two sides are congruent, so we can classify it as such by the definition. Very good. All right, any questions with that? Show me thumbs up if you got that all the way through. And once again, you could have flip-flopped steps 2 and 3. Good. Okay. All right, so let's take a look what we're doing today. Like we said last class, we flip-flopped our lessons. So today we're going to be doing proofs. This is the last class we did our special parallelograms. Now, if you take a look at your assignment sheet, what's happening next class? Yeah, time for a quiz too. So next class we will have a quiz, and then we'll do more with our trapezoids and heights. I think that's what you guys need to do. Yeah. So next class we'll do quiz, and then trapezoids and heights properties. So just keep that in mind. I do have your last quizzes graded. The grades are up on 6. Unfortunately, I cannot give it back to you yet because I said to go out and take it. Our next class. So your special parallelograms and proofs. Is there anyone that did not get a copy of the notes? Okay. Now notice it says complete the following proofs on a separate sheet of paper. Get out that separate sheet of paper. Do not try to squeeze it on here. Some of these get really long. So get out a separate sheet of paper. But that way you have the picture to refer to. You don't have to copy everything down from the board, but you'll have some space. And notice I have numbered the proofs for you, so as we go through and do them, I highly recommend you number them so you know which one we're doing. Okay, let's go ahead and just take a look at this first one. This first one's not too bad. The reason why some of these get long is because we might have to prove segment pieces are congruent to each other or angle pieces are congruent to each other. And like we've had in previous proofs, anytime you have to use that segment addition postulate, it usually is about 5 steps. Or the angle addition postulate to show 2 pieces are congruent. So that's what makes these longer. So the big idea is not bad, but sometimes the execution is a bit lengthy. But this first one is pretty reasonable, so we'll start off with that. Kind of similar to the one that we had for our warm-up. But notice that a lot of these are shapes that are special parallelograms, so you'll see rectangles and rhombuses are in here. And I think there's one with a square. So now that we know those special properties of them, we have an easier time doing this. Okay. So we're just going to start out with this first one. comes back to us. Alright, while I try to get the smartboard to function with me, go ahead and take a look at the proof. Kind of think through the big ideas of what you would do for it, and then we'll come back to it. Let's see how we did with this. Okay, so we have HJLM as a rectangle. So we're probably going to need to use our properties of rectangles. And they tell us that KJ. Oh, we don't have this. Oh wait, I unplugged. Alright, we have KJ is congruent to NM. Okay, and then they want us to prove that HK and LN are congruent to each other. So if HK and LN are congruent to each other, what type of shape are we hoping that that's going to be? Although actually, we don't even have to worry about that shape there. So I don't know what we're saying about these shapes here. Yeah, they're triangles. So look at that. We can actually go back to our congruent triangles, and if we can get those triangles congruent, then we can get those little pieces are congruent. And a lot of times we have our congruent triangle shows up in our special parallelograms because that's how we can prove some of our properties. It's not always going to use them, but don't forget about your congruent triangles. Alright, so we have HJLM is a rectangle, and KJ is congruent to NM. Alright, so what was the next step that you guys took with this? Knowing that HJLM is a rectangle, what you guys say from there? Go ahead and stop now. Good, I like that. HJ and LM are congruent. And again, that's opposite sides of rectangles are congruent. You could have also said, well, actually, since this is a rectangle, we want to refer back to that shape that it gave us. So opposite sides of rectangles are congruent. Yeah. And what can we do next from here? Alan, what'd you do next for this? We've got our two sets of sides congruent, and we know we're trying to get those triangles to be congruent. What else could I say? So coming up. Good, angle M is congruent to angle J. And you didn't have to worry about saying that they're right angles. For here, we just needed that they were congruent. We know that they're right angles because it is a rectangle. So you could have said angle M and angle J are right angles by definition of rectangle, and then you could have said angle M is congruent to angle J. But since we know opposite angles are congruent, we can go ahead and just start off by saying that they're congruent. So opposite angles or rectangles are congruent. Perfect. And now we've got that side angle side, so I can say triangle NML is congruent to triangle. What matches up with N? What should I be using? Which vertex of my other triangle? K. Good. So we've got then K KJH. And that was side angle side. And then finally we can take it home and say HK is congruent to LN. And Matthew, what's my reasoning for that very last piece? You're close. Once I know congruent triangles, I know their pieces are congruent. What's that acronym? Go ahead, Molly.
Two things congruent parts of congruent triangles are congruent.
Very good.
And for number 4, you wrote HJ.
Oh, that's not good. Let me fix that. So we've got CPCTC for that last one. Congruent pieces of congruent, corresponding pieces of congruent triangles are congruent. Thank you. And that should be, all right, now I messed myself up. KJH. Thank you. Good. So 5 steps here, and once again, you could have flip-flopped steps 2 and 3. Those are they're independent of each other. They do not rely upon each other, so you can flip-flop those. All right, questions with that one? Okay. Let's go to a bit more challenging ones. So let's go ahead and take a look at number 2. So take a look at that picture. Read what it's asking there. So this one, the big ideas is not bad, but because we do need to use some same and addition posture with it, it does take a bit of time with our steps. Okay, so at first you might be like, oh, that's easy, that's obvious, just make sure you're not skipping all the tiny details. So we have ABCD as a parallelogram. ABCD is a parallelogram. W is midpoint of AO. X is midpoint of BO. Y is midpoint of CO. And finally, Z is the midpoint of DO. Okay, so let's fill in all of that information that we have from there. So focusing on what I know about midpoints. And they're wanting us to show that WXYZ is a parallelogram. So I'm going to just kind of draw that in there so we can visualize that. WXYZ is a parallelogram. Now, they told us that the big shape is a parallelogram and that these are midpoints. So we know that those are going to be congruent. And I know that these are going to be congruent. We're good so far? Now, if diagonals bisect each other, we know that essentially these will also be congruent to that over there, but we have to kind of get there for that. And likewise, these are congruent to that. But let's go ahead and start off just by translating what that midpoint means for us. So once again, this is going to be a lengthy proof, but the big ideas are not bad. All right, so keep in mind that ways to prove it's a parallelogram, we can say opposite sides are congruent, opposite angles are congruent. If I look here, I don't really have much about my angles. I could state something from my original parallelogram, but as far as the additional information, I have more information about my diagonals than I do about angles or sides. So what is a way to prove that's a parallelogram based upon the diagonals? What has to be true about diagonals? Yeah, diagonals bisect each other. So if I could show that WO and OY are congruent and ZO and OX are congruent, then I've got it. But like I said, it does take a bit of work. We know that our big diagonals have been bisected, so we're going to need to use that and then also some same condition function. So we know we're headed in the direction of diagonals, so let's go ahead and work together with that. So we've got the midpoints, let's go and translate that. So I've got, because W is midpoint, so I know AW is congruent to WO. So just working my way around, I know OX and XB are congruent. And I've got OY and YC are congruent. And I've got OZ and ZD. So since those are our midpoints, we can say all those little pieces are congruent. I notice I can't yet make that connection between like A, W, and YC yet, but that's what we're aiming for. What would be my reason for step 2 here? Go ahead, Bree. Yeah, definition of midpoint. We know that that was true because they were the midpoints. Yeah. Alright, and we said we know that we're going to need to get those individual diagonal pieces to be congruent to each other. So let's go and talk about the big diagonals. Because if I can show that this big one and these ones are congruent and they both got cut in half, we should be able to get from there that the little pieces are congruent. So let's go ahead and go with that one next. We've got AO is congruent to OC, and likewise DO is congruent to OB. And once again, that's from diagonals of parallelograms bisect each other. Okay, so we've had kind of a couple key things here. We've got our definition of midpoint and our diagonals bisect each other, kind of our big ideas. Now we have to go into the nitty-gritty. We can see and reason through logically that WO and OY are congruent. That's what we're aiming for here. If I can get there and do the same thing with ZO and OX, if I can accomplish those two things, then we're practically there to showing that it's a parallelogram. Now, like we said, we know that because my diagonals got bisected, these chunks are equal to each other, and if they each got cut in half, then certainly these chunks must be equal to each other. But we have to show that through segment addition postulate, so that's what's going to take a little bit of time. So we've got our big ideas here, we know where we're heading, but let's deal with the nitty-gritty of it. Alright, so let's go ahead and start off by saying we know that AO is made up of AW and WO. So we're going to basically translate each of these into our segment addition postulate. So it is going to take some steps. We'll deal with it. Alright, so I know AO is made up of AW and WO. Likewise, OC is made up of OY and YC. So we're really just setting up what the bigger segment is made up of for each of these. Okay, and then we've got DO. It's made up of its pieces. DZ plus ZO. And finally we've got OB is made up of OX and XB. Alright, and this was again just segment addition postulate. So once again, I know that these big pieces here are congruent, but I want just these little pieces to be congruent. So I've got to somehow tie those together. So I rewrite the big pieces as a sum of the smaller pieces. And we're far enough in the year now, segment addition postulate, an angle addition postulate. I'm fine with you using it either congruent pieces or measures equal. Either way, you no longer have to go back and forth, translate it between the two. You can start off by using segment addition postulate as congruent rather than measures equal. Okay. So now that I have the larger diagonals are made up of the smaller pieces, I want to go ahead and show, we're trying to get WO and OY to be the same. So if I can get these to be made up of just WO and OY, then I have those two are equal, and we can show that they are equal. So notice here, I already have AO and OC are congruent. So I can set these two together, so these two equal to each other. But I want to do some substitution, so I'm left with just WO and OY. So let's go ahead and do some substitution there. Again, I want just WO and OY, because those are the two that I'm trying to prove congruent. How can I get rid of AW and YC? How can I get rid of those?
Or you can substitute W.
Good. From back up here to definition of midpoint, I know that AW is congruent to WO. I know that OY is congruent to YC. So if I can just do some substitution, then I have them in terms of the two pieces that I want. Alright. Only on step 4 units. So once again, big idea, not bad, just a little lengthy. Alright. So for AO, I wanted WO and OY, I believe. Okay, I'll just use that. So I'm going to replace AW with WO. WO plus WO. Because again, I wanted only WOs. And then in OC, I wanted only the OYs. So OY plus YC is the same thing as OY from up here. So I can replace each of those. Are we okay with that? Questions on why we're doing that there? Okay, so we need to do the same thing for our other diagonals. So when I take a look at DO and OB, for DO, which piece do I want to keep? Do I want the DZ or the OZ? Take a look at your picture. Do I want DZ or OZ to stay? So I can say it out loud together. OZ, good. So I want to keep my OZ here. Okay, so I'm going to go ahead and replace that. Since we're just doing the same operation here, we can put it all in one step. So I want OZ, which we know DZ is congruent to it, so I can say OZ. OZ. And then in OB, which piece do I want to keep there? OX or XB? Anyone can answer. OX, very good. So for OB, I want to keep OX. And XB is the same thing as OX, so we can go and substitute that. Alright, so again, a lot of writing because we have to do it for all the 4 pieces here. But it was the same reasoning for each of those. What was my reasoning for this? What did we do there? Good, Megan. Yeah, just substitution here. Very good. Okay. Now we can either simplify and then set it congruent to each other, or set them congruent and simplify. I think I'm going to go ahead and simplify what I'm here. So I have AO is congruent to 2WO. Maybe I can save some space now. OC is congruent to 2OY. DO is congruent to 2OZ. And we have OB is congruent to 2X. Alright. Now we can go back up to what we had here in green. The large diagonal pieces were set equal to each other. So I have AO is congruent to OC. So now let's go ahead and put back in what we had for that. So AO is congruent to OC. So instead of AO, I'm going to write 2WO. And AO is congruent to OC. Instead of OC, I'm going to write 2OY. And then once again, looking at my green here, I have DO and OB are congruent. So I'm going to replace those with our new equations we just found. DO is congruent. Whoops. I want to replace DO, which is 2OZ. It's congruent to OB, which is just 2OX. Alright, questions on that? What did I do there for step 7? And oh, actually, I forgot to do step 6. What technically did we do for step 6? What's our reasoning for step 6? Anthony? Yeah, substitution. We just simply combine like terms or simplified, which is substitution. And then for step 7, what did I do? How did I go from step 5 to from step 6 to step 7? What did I do there? I know we went back up to the green, right? We took our equations here and replaced them in the green. So what would that be? What would be my reasoning? Yeah, substitution again. And you'll notice that when you have to use segment addition postulate to prove little pieces are congruent, it's a lot of substitution. Okay, let's keep going. Again, our big idea that we're trying to get at here is showing those small little diagonal pieces are congruent. We're trying to get this up here. We're trying to get WO congruent to OY and ZO congruent to OX. Well, we look like we're pretty well set up there. What should my next step be? What should I do after step 7? What do you think? What should we do after step 7? Yeah, let's divide by 2 on both sides, because then I can say, all right, guess what? WO is congruent to OY. OZ is congruent to OX. And we just did our division there. Division code, very good news. And now we have finally accomplished that big idea that we were aiming for in the beginning. Now we have to finally make our formal statement here in the end. But if we take a look, we were trying to get these little pieces of our diagonals to be congruent, which is that big idea I have here circled in black. And so we finally got that accomplished. Now that I know that these little pieces of my diagonals are congruent, now I can say it's a parallelogram. So now I can say that little parallelogram, that little shape there, is a parallelogram. So now I can say WXYZ is a parallelogram. And what would my reasoning for that be? Bree, what would my reasoning be for number 9? I finally just showed that our little diagonals are congruent. Which way can I use to say that it's a parallelogram? So be careful, if it was a rectangle, diagonals would be congruent. But for just parallelograms in general, what's our property for diagonals of parallelograms? Go ahead, Anthony. They bisect each other. So if I have that WO and OY are congruent, that means they got bisected. And if OZ and OX are congruent, that means that got bisected. So we have that diagonals of parallelograms bisect each other. And that allows us to say that WXYZ is parallel. And although it took us 9 steps, really steps 4, 5, 6, 7, and 8 were all used to go from segment addition postulate to show that these little pieces were congruent. So in terms of big ideas, we only had really steps 2, 3, and 8 were kind of our big idea there. But it took, again, a lot of steps to get to show that these little pieces were congruent. So if you have to use segment addition postulate, that's fine. Just know that that will create your proof to be a little bit longer. So if you notice, it took what? 1, 2, 3, 4, 5 additional steps. So keep that in mind. If you're using segment addition postulate, it shouldn't take just 2 steps if you're trying to prove those little pieces. Alright, questions with this one. This is one of our longer ones here. I want to make sure you got some exposure to this one. Don't be alarmed if it's getting pretty long. It's definitely possible. Questions with that? Okay. So let's take a look at what we have next. Alright, so ABCD is a parallelogram. N is the midpoint of AB, so we know this here. And N is the midpoint of DC, so we know this here. And then they want us to show that AMCN is a parallelogram. So they want us to show this guy here. It's a parallelogram. Alright, now once again when we look at this, it says AM and MB are congruent and CN and ND are congruent. But if my big shape is a parallelogram, what do I know about opposite sides? If this big shape here is a parallelogram, what do I know about those opposite sides? Go ahead, Anthony. They're congruent. I've got that these are congruent, I also have that they're parallel. But if these are congruent, then surely the little pieces cut up are the same as well. But once again, segment addition postulate is what we have to use for that. So I want you guys to go ahead and try this one with your shoulder partner. And perhaps you might do it a different way than someone else nearby you. But go ahead and talk with your shoulder partner, work with one another. How can we get to show that AMCN is a parallelogram? This is one of our longer proofs, so don't be alarmed if it takes longer. But go ahead and give it your best shot. We'll go through the nitty-gritty of the steps for it. So go ahead and scoot your desks together so you can work with one another. And Alan, I'll actually have you come over and work with Matthew because he doesn't have it today. Alright, let's go ahead and see how you guys did with this one. Again, we talked about how most likely, even though you might do it a different way than what we're about to do it, we're probably going to have to show that AM and NC are congruent, or that NB and DN are congruent, depending on which method you use. Which requires us to once again use segment addition postulate and say the whole sides are congruent to each other, that each side is made up of 2 pieces added together, do some substitution, some simplifying, set them equal, and finally get those little pieces are congruent. So once again, when you have to go about that, using segment addition postulate to show a couple small pieces are congruent, it does take about 5 more steps. So let's just go and take a look at that. Let me get it to the actual one. Alright, so again, we can see that here. So for this one, I took the approach of doing congruent triangles. And I think I heard some of you guys talk about that. But this triangle, congruent to this triangle, allows me to then finish out the opposite sides will be congruent. So as you can see, once we've defined from the fact that we're the midpoint, step 2 is using our definition midpoint to say those individual pieces are congruent. It took steps 3, 4, 5, 6, 7, and 8. So it took, once again, about 5 steps to show that those little individual pieces are congruent. Okay, so then once I had that, I have MB and DN are congruent. And likewise, AM and NC are congruent. So right now, with just that, I have opposite sides are congruent. Now, using our other pieces being congruent, and then the fact that we have opposite angles of a parallelogram are congruent. And I think I left off... I think I forgot to put in here opposite sides of the parallelogram are congruent. So we have AD and BC are congruent to each other. Oh no, sorry, I've got that instead. Okay. So now I can say that these triangles are congruent by side, angle, side. Then by CPCTC, these opposite sides are congruent. And now I have opposite sides of a parallelogram are congruent. Raise your hand if you went that route with showing those triangles congruent together. Very good. Now another method that you could have done is once we have shown that these segments, these little pieces are congruent. So again, we still had to go through that segment addition postulate. Nope, okay. I'll just use the mouse here since it's not going to work with me. Once we've shown that these pieces are congruent, remember one of our ways we can show that it's a parallelogram is opposite sides are, one set of opposite sides are both congruent and parallel. So after I've shown that A, M, and NC are congruent, if I went ahead and said, hey, since this is a parallelogram, A, M, and NC are parallel, then you could have gone ahead and saved yourself a couple steps and said the entire thing is a parallelogram. Did anyone happen to use that method? Very good, Ryan. So keep that in mind. It's not a common one that you can use, but sometimes you can sneak it in there and make it a little bit quicker for you. So once again, we still had to do all the steps 1 through 8 to show that A, M, and NC are congruent, but then you could have said opposite sides of parallelogram are parallel, and then you have this as a parallelogram. Questions with that? Very good job persevering on that one. Okay, so if we take a look at our fourth proof here, so we have A, B, C, D is a parallelogram. AN bisects angle DAB, so we have these are congruent. And CM bisects angle BCD, so these are congruent. This is going to be one of your longer proofs, so just put a note to yourself that this is a long proof. But then 5 and 6 are back to being not too bad of ones, okay? So just make yourself a note. 4 is a longer one. But 5 and 6 aren't too bad. Okay, so notice that your homework is to finish these proofs, so these ones from class, and then the 3 in the textbook. Now, notice it says for the textbook one, you're proving these theorems, so don't use them. Those ones are pretty short. Okay. So, again, your homework is to finish these ones and do those proofs in the textbook. And next class, we do have a quiz over our special parallelograms of proofs. Make sure you're ready for that.